So I just want to come back for a minute to finish up the example from part one. We talked about how if you have a graph of power versus time, that the area underneath is equal to the work done. We also made a statement that the work is equal to the integral of power with respect to time. And this is useful if the power is changing. So if we look at come back to this example again that we talked about, the same example, you could say in this case you have a power which is following a function. It begins at 0, it ends at 100, and it takes 5 seconds to get to 100. So the function for power here would be something like this. The power is equal to 20 times t plus 0. And the 20 would be in watts per second, so that when you multiply by time in seconds, you'll end up with watts of power. So I just want to show you that if you integrate that function, from 0 to 5 seconds, you'll get the same answer that we got before. Okay. So doing the integral, you have 20 times the integral of t dt from 0 to 5. And of course, that's 20 times t squared over 2, evaluated from 0 to 5. And so 20 over 2 is 10. So we have 10 times 5 squared minus 0 squared. And that gives the same answer as what we got before. So it's a good practice here with integration. And you should be able to do that at this point for simple integrals like that. One last thing I wanted to share with you also comes back to the idea of our definition of power being written as a derivative. So instead of just saying that power equals work over time, we can say it's equal to dW over dt, where these are basically calculus small values of work and time. Okay. And if we write it that way, you can basically say, well, I'm gonna focus on the work part of that, right? Because that's what the derivative is acting on. The d dt is acting on the work part. But work is really just going to be force times kind of your displacement, right? So the definition of work is the dot product between force and displacement in a certain direction. So see what I did here is I'm replacing work with the definition of work that we learned at the beginning of the unit. The reason that I write it that way is because you can actually factor out the force. As long as the force is not changing with time, it comes out as a constant. And the derivative acts just on the dx. Okay? So let's just write this, that we assumes that you have a constant force. That's important because that allowed us to do this one, to pull that force out in front. But the bottom line is that you end up with a different way of finding power. Do you recognize this? That power is equal to force times dx dt. Well, what's dx dt? That's actually just velocity. Okay. And so this is a really handy formula for finding power. It's the power that's basically being exerted by a constant force when the object is moving at a particular velocity. Okay, so again, this is for constant force. I guess we already wrote that, but the idea is now the object is moving at some velocity. And so it just allows us to solve for power in a different way, because sometimes in problems you know what the force is and you know what the velocity is, and you want to find the power. By the way, I'm also going to point out that this is actually a dot product. So this is a vector, this is a vector. And so really technically, it's like you would have the magnitudes of these two vectors and then you would multiply by the cosine of the angle between them. So if the object is moving this way, but the force is applied this way, and that's your theta, then the part of the force that does work is the part that lines up with the velocity. So it's the same deal that we had with work, okay, so that we have a dot product that's happening here. Okay. So a quick example would be, like, let's say that I'm swimming. There I go. There's the water. And let's say that I can swim at a velocity of 1.2 meters per second. And I can keep swimming at that rate for a while before I collapse. And then the reason I'm moving forwards is because when I'm swimming, I'm cupping my hands and I'm pushing water backwards, right? So here's some water. I push it backwards with some force. But that water actually exerts a forwards force on me. And so the question would be, how much work is that force doing on me? I'm sorry, at what rate am I doing work if I'm pushing with a certain force and I'm moving at this speed? Well, let's make up a number. Let's say that this force is equal to 100 newtons. That's an average value, right? Because nobody swims by pushing with a perfectly constant force. But maybe I can push with 100 newtons on average, and I can keep myself moving at this speed. In this case, the power that I would be using could be found by multiplying force times velocity, or 100 newtons times 1.2 meters per second. And of course, that's 120 watts. And that would be the power that I'm basically putting into pushing the water backwards as I'm swimming. Okay? So that's the idea with power. It's just a different way of calculating it. But in many problems, you're going to have this situation where you know force and velocity, and it's just really fast to get to the power that way.